we need to dig into Chapter 7 and review some of those problems to prepare for next Tuesday. All right. Based on our review document, we'll look at the first three. Start with number 1. Good place to start. When ignited, uranium compounds burn with a green flame. The wavelength of the light given off by this flame is greater than that of. So it says the wavelength of this uranium compound. They want to know, is it, which one is it greater than of those selections? So we want to know that one's greater than which one. Okay. So in order to do that, I like to draw pictures. So here's our continuum of a spectrum. So we've got visible in here, expanded just to make a little more room for my writing. And uranium is giving off this green light. So it's, if we go a long wavelength this way, that means red's on this end and violet's on that end and green's about there. So this is that's our starting point in comparison with the others. Okay, red light is here. We want a wavelength that's longer. So the wavelengths get longer this way. And what comes after red is infrared. After that, microwave. What comes after that? Radio. Right? Okay, from the other direction, ultraviolet on this end. Let's see. My mind's gone blank. Go back from this direction. Gamma on this end. X-ray. There we go. Okay. So the wavelength of green light is going to be longer than anything on this end. So let's see if any of those are there. Let's see, gamma rays. Wait a minute. I'm looking at the wrong one. Wavelength of light given off by this flame is greater than that of. Okay. It's not greater than red, not greater than infrared, not greater than radio. It's greater than ultraviolet. And red, orange, yellow. It's not greater than yellow either, so ultraviolet's the answer. Longer wavelength. Okay, I'm gonna leave that up there because it looks like I might need it. 2. Somebody put something on this board that's making a mess. Which form of electromagnetic radiation has the longest wavelengths? Well, there's our thing. The longest wavelength is way out here. So do we have radio? Yeah, there's radio. See, that's the longest one. About 3. Which of the following frequencies corresponds to light with the longest wavelength? Okay, if the wavelength gets longer, remember this? Inverse proportionality. Wavelength gets bigger, frequency gets smaller. Smaller number. So if the wavelength is longer, that means the frequency is just the other direction. The longer, I should say not longer, say the greater. Greater or larger value for frequency is down here. So the short wavelength means longer frequency. And let's see, the longest wavelength would be the smallest frequency. So first place I'd look is with the powers of 10, right? And if you had two of them with the same power of 10, then you go to the coefficient to break the tie. So the smallest number for the frequency value is right here. And it's the only one. So 5 is the smallest number. 4.12 times 10 to the 5th is the smallest frequency. And that corresponds to light with the longest wavelength. Okay. Let's see. Let's skip down to, we don't skip very far. We'll go to 6. I bet you've been using furniture policy. Okay, let's see if I can do this. Yeah, there we go. A line in the spectrum of atomic mercury has a wavelength of 254 nanometers. So the wavelength equals this mercury, 254 nanometers. When mercury emits a photon of light, this wavelength, the frequency of that light is what? Well, we use that same formula, right? This is their relationship. So if that wavelength is this value, and you want to know the frequency, then just put the wavelength on this side. Okay? You can calculate the frequency. So you need to know 2.9979 times 10 to the 8th meters per second. And then the wavelength is what? 254 nanometers. Right. If we're going to cancel that meters, we got to change this to meters. All right, so here's how I do it. What does nano mean? Okay. Pull that nano out. 10 to the minus 9 meters. Right. And you can just plug that number straight into your calculator. You don't have to convert it to scientific notation. You say 254 times 10 to the exponent minus 9. Now, if we did put it in scientific notation, we move these two this way, and then make that minus 7 meters. And check our units. What are the units of measure for frequency? Well, nominally hertz, but that's reciprocal seconds. So this seconds is in the denominator. This one's in the denominator too. So those meters cancel, and you got the right units. So once you run that calculation, this is going to be, let's see, 10 to the 15th. And this is going to be something over 1. Right, there's 10 to the 15th. That would be my guess, even if I didn't have a calculator. I'd say that's the best answer. Except that, oh yeah, here's the catch. None of these. So you'd have to calculate it to be sure it was that value. Sneaky. In this case, it is C. All right, that's 6 to the 8. Yeah, I better scroll backwards. Okay. Green light. Green light can have a wavelength of 543. 543 nanometers. I like that question. The beginning of it. Green light can have a wavelength of 543 nanometers. That tells me it doesn't have to be 543. That is green light, yeah. But how do we know it's green? Because our eyes, our brain tell us so. And they respond to more than one wavelength to give us green color, right? So it could be green can have a wavelength of probably 542 or 544. But in this case, we're given that value. What's the energy of the photon of that light? What formula do I need? Planck's. Energy equals Planck's constant times frequency. Or if we use the conversion, Planck's constant C divided by wavelength. Okay, I just took the equivalence of, speed of light equals frequency times wavelength and just solved for frequency and plugged it in there. That's all that was. That way I only have to do one calculation. Just put in Planck's constant, which I can't remember, 6.63 something. That's why I put it in here. 6.626 times 10 to the 23rd joules seconds. Okay, and speed of light 2.9979 times 10 to the 8 meters per second divided by wavelength. And here we need meters again. So I'm going to use that same trick. 543 times 10 to the minus 9 meters. There we go. Okay, now will that give us the right units of measure? Okay. Denominator, numerator, cancel. Numerator, denominator. Right. Seconds cancel. Yeah, we get joules. That's a unit of energy. So if we resolve that equation, this is the thinking part. The rest is just crunching numbers. And hit the wrong button. So we should end up with 3.66 times 10 to the minus 19 joules. That's the energy of one photon of that green light. I was going to say something else. That's good. That was number 8. Okay. Let's see. Skip down to 11. There's scroll. We're going to chop it off. By next semester, I'm going to have one of these as a scroll one. Number 11. How many of the following is or are correct? Okay, so it looks like we're going to have to look at each one of them, see which one's correct. Four of them, right? Okay. The importance of equation E equals mc squared is that energy has mass. That's one way of putting it. I mean, the formula itself says energy equals mass. And the proportionality constant is the square of the speed of light. Right? That's a constant. So I don't know if I've said this before, but the thinking part of this whole process was to recognize that E is proportional to mass. They're related in some way. That was Einstein's thought process. So what he knew that mass was in kilograms and energy was in joules, right? So you can't say they're equal to each other just like that. You need some form, you need a proportionality constant. And in order to make that happen, he needed c squared. Okay. Now, why did he know this? Or why? Maybe he didn't know that, but why does this confirm that that is a valid unit of measure? Well, what's energy? Kinetic energy is 1/2 mv squared. That has mass in it. I mean, that's what we want. So if this is going to be joules, what's this equal to? Well, mass is in kilograms, right? And velocity squared is in meters per second squared. So there you go. Both those taken together give you joules. I'm not sure if that was his thought process, but it validates anyway. So one is true. Electromagnetic radiation can be thought of as a stream of particles called photons. Yeah. What evidence did we study that said that's true? I'm in trouble with my brain today. I can see a picture of it happening. Photoelectric effect. Right? That one's true. Electromagnetic radiation exhibits wave properties. Yeah, in fact, before the photoelectric effect was discovered, that's all there was to go on, was wave properties of light. It behaves as both. Energy can only occur in discrete units called quanta. But yeah, that's another way of saying photons. Okay, so they're all true. All four of them. All right, I think I need to go down to 12, 13, 14. 12, 13, 14 are based upon this table. Following a list of observations, choose the one that most clearly supports the conclusion for each of the ones. Okay, so let's go down far enough to get at least 12 and 13. So for 12, electrons have wave properties. How do we know that? We know electrons have wave properties because they exhibit what? Characteristic. Right? I'm sorry? Oh, yeah. Diffraction. In fact, that's the only one in here that relates to waves is diffraction. The rest of them are particles. Right? Emission spectrum of hydrogen is quantized light with the movement of an electron from one position to another. Photoelectric effect, we already mentioned that one. That can only happen with particles. Cathode rays are particles of light. Electrons, excuse me, not light, electrons. And diffraction, where do we use diffraction? If electrons have wave properties, is this just a curiosity of science? Or do we actually make some practical use of it? How about the electron microscope? If you accelerate electrons to a high enough speed, which means very high voltage, you can get their wavelengths very, very short. That's based on Broglie's. Let's see how much about that. I think it's a lot small. Broglie's equation that relates mass and velocity. See, I think I have it in useful information. Where did it go? There it is. Mass times velocity. Planck's constant divided by mass times velocity will give you the wavelength of any object moving at a given velocity. So if I'm going down the road at 60 miles an hour, I guess you have to consider the mass of the car too. Me and the car. Multiply those together and divide it into Planck's constant, I will have a wavelength. Wave property. But if your mass is really, really, really small, and you speed it up really fast, then you can make this number big. And that decreases the wavelength. And there's a limit, they call it the diffraction limit for light in light microscopes, where you can't even, there's a theoretical lower limit for what they call the resolution, the separation of two particles in that field that you can discern as two and not one. That using astronomy too. But in microscopes, there's a limit to how small a structure you can discern with light. So just use electrons, and they're small mass, you can make them really fast, and you can get that wavelength way down below light wavelength. And you just fire it at your target, and then focus it. Right? You can't use lenses, typical lenses, glass lenses. It doesn't work that way. So you focus it with magnetic fields, and then you focus that image on a fluorescent screen, and you have a microscope, a pair of binoculars, and you just look at it. Or you have a camera now that takes a picture of it. So that's a practical use of the wave characteristics of electrons. Electromagnetic radiation has wave properties. Well, yeah, same reason. Diffraction. Right? Do you remember what diffraction is? I like to draw pictures. You have a, actually any edge will do it, but let's make it a slit. Right? You got that little gap in there. And if there's a wave front moving here and it strikes that object, this serves as a point source for a new wave, and it just propagates out like that. And the reason we know that it's behaving as a wave because we have detectors out here. Right? If it were a particle, if light were a particle, it would go straight through there and bang. Only those detectors would pick it up. You see nothing out here. But since it's a wave, we see the bright spot in the middle, but dimmer and dimmer and dimmer and dimmer light should go away like that. Okay. The other way you can pick it up is instead of one slit, you put two. So now you've got another wave propagating out here. And if these lines are the crests, then wherever they meet, they constructively interfere. And wherever a crest meets a trough, they destructively interfere. And there's nothing there. So once they find your detectors over here, you'll have a bright one here, then you'll have one there, one there, one there, there. And they get dimmer and dimmer as you go out. It's a diffraction pattern. We use that in optical instruments instead of prisms. We use diffraction gratings, which have very fine spaced lines, and each line, each dip in that surface serves as a point source for another wave. And if you turn it right, then the different colors, just like prisms, the different colors respond differently with their own diffraction pattern. So with the grating, you can shine light from an element on there, and it will spread out here, and it'll have line spectrum, characteristic wavelengths. And if your instrument is set up right, you can have maybe one detector over here, and as your grating rotates, it'll bring different wavelengths past that detector. Right? And if you got a mixture of elements, each one will have a characteristic wavelength. And one of them is stronger than the others. Plus, you try to pick the one that's not interfered, not very close to other elements' wavelengths. When that line will pass here, you get a reading, and you can quantify how much of that element is in your sample. That's called a scanning spectrometer. Oh, I'm wasting too much time. We got to get through this thing. Okay, 14. Yeah, we want to do 14 also. So electrons in atoms have quantized energies. What's the best evidence for that? Quantized energy. If the electrons are quantized, then that means they can only have certain energies. And if they transition from that quantum position to a different quantum position, they either emit or absorb light of a particular wavelength and the energy. So the energy of movement of an electron between levels corresponds with a wavelength of light because it's translatable into energy. Okay. All right, that's 14. Let's see, what do I have next? That goes wild with 10. 15. And we can still see that one. Spacing between atoms in a crystal is on the same order as the de Broglie wavelength of accelerated electrons. Oh, this one refers to that one also. Okay, so we're still talking about yeah. We can tell the spacing between atoms in a crystal. They're packed in there like that. And if a wavelength impinges here, some of them will be reflected there, some of them will pass through and be reflected at the next level. And what you do is because there is space delay in their waves, they form an interference pattern out here. Diffraction. And actually it looks like this. It's like a peak. Actually, it goes more like this. There's one really big one in the middle and then smaller ones. So you look for that maximum. And that's due to the fact that electrons have wave properties, which means that is a diffraction pattern. I've used that to investigate clays and soils. Tell what's the spacing between the atoms or the molecules in the layer of a clay. It has a direct bearing upon soil chemistry. Okay, it was a pretty ancient instrument, but I was a student, so I didn't mind. Let's see. Yeah, 16. The 4 lines observed in the visible spectrum. Emission lines of hydrogen tell us what? We've actually covered that already, right, in one of the previous problems. That tells us that only certain energies are allowed from the electron in the hydrogen atom. If an infinite number of energies were allowed, say if you add energy to the electron, and it just moves up here. Add a little more, it moves up here, moves up here. Add more, it moves up there. Or if it does the other direction, if it has a continuous available energy amount in its environment around the nucleus, then what type of spectrum would you see? Continuous. Right? If you have continuous variable energies, you'll see a continuous light spectrum. Right? But we don't see that. We see line spectrum. It's limited to certain energies. That's why only certain energies are allowed for the electron in the hydrogen atom. That's the best answer. How about 17? What do we got there? Oh, now we're going to get into quantum numbers. For which of, well, we're sort of there. We're still talking about Bohr here. This is the principal quantum number. But when Bohr was doing his work, he only had that one number. And it was related to energies. Okay, so let's stick there. Which of the following transitions does light emitted have the longest wavelength? All right, if you got, I like to think of it this way. If I can write it. The longest wavelength corresponds to the lowest energy. The longer the wavelength, the lower the energy. So what do you need for an electron transition in an atom to give you the lowest energy? You need the shortest jump between levels, don't you? So remember when we saw that picture of energy levels? Let's see, energy system. So if 1 is here, and 2 is here, and 3 is about right here, and 4 is about right there. Is that the ones they gave us? Yeah. 4, 3, 2, 1. Which one of these is the biggest jump from 4 to 1, right? And maybe 3 to 1 would be a pretty big jump, but less. 2 to 1 would be another big jump, but less. The smallest jumps are up in here, between these levels. So anything jumping to the 1 is out. C and D can't be it. 3 to 2, okay, that's a jump. How about 4 to 2? That's too big. 3 to 2 is still better. How about 4 to 3? There we are. 4 to 3 is the shortest jump in that group. All right, let's see. 18. When a hydrogen electron makes a transition from N equals 3 to N equals 1, which of the following statements is true? We're going from N3 to N1. So which one's the higher energy? This one. If you're going from higher to lower, that means you got excess energy. It's got to go somewhere, right? Conservation of energy. So where does it go? It's emitted. It has to emit energy when it goes from N3 to N1. So let's see which one matches. Energy is emitted, that's true. It can't be emitted and absorbed at the same time. So 2 is out. The electron loses energy. That's true. It goes from a higher energy to a lower energy. So 3 is true. 4 can't be true because 3 is true. Electron cannot make this transition. I was searching around for a placeholder. Right? That's just a stupid statement. Of course, an electron can make that transition. 4's already proved it. Oh, okay, so 1 and 3. So that's B. All right, that was 1821. See how we're doing. 21, here we go. Which of the following is incorrect? So that's why I put that in italics. Try to draw your eyes to that. It's easy to be, moving along in your exam and just read. We're not speed reading here. We're detail people. Which of the following is incorrect? Okay, so we've got valid proposals for each one. That means we've got to look at each one to find out which of the following. Actually, if we read down through there and find one of them incorrect, our job's done. Because we don't have any multiple answers down here. Okay, the emission spectrum of hydrogen, 21. The emission spectrum of hydrogen contains a continuum of colors. I don't think so. Right. We've already proved that it's a line spectrum. So we're done. The rest of them have to be true. In the interest of time, we'll not beat that horse today. Let's see, 22. Which of the following statements describes the Heisenberg uncertainty principle? Remember that one? What did Heisenberg say? He says, represent this as a deviation in position. So the smaller this is, the closer you are to knowing where something is. That's what that represents. And then this one is momentum, mass times velocity. Right. So the deviation here, if you make that really, really small deviation, that's not an absolute amount, that's a change. So the error, I think that's what it stands for. The error in momentum is very small. That means you know how fast it's going and how much energy it has. Okay? Now that has to be I think it's less than. Within Heisenberg's formula. No, I think I left it out. Oh well. Let me see if my memory serves me. I think it's less than or equal to Planck's constant over 4 pi. I believe that's right. I have to look it up in your book, Rory. Go back in it'll be in PowerPoints. See if I got that right. What we mean here is if we're talking about a single particle, like an electron, then the mass is not going to change. So the deviation here we're talking about is really deviation velocity. What it says is for very small particles, this is extremely small, and the velocity is probably pretty high, then you can't know both of these with any certainty at the same time. If you know where it is, you don't know anything about its velocity or its energy. If you know its velocity and energy with precision or accuracy, then you don't know where it is. Okay? So this leads us to the conclusion that when you're trying to describe the electron in its position around an atom, which one is more important to you? Well, sometimes we split the difference, right? Our wave functions gives us probability. Like the electron is going to be somewhere in here, maybe 90% it'll be in this space. So there you're kind of hedging on this one. It's really more important to know what's the energy of the electron. And particularly when we start writing the structure, the electronic structure of an atom, the energy is much more important. Although the wave function, Schrodinger's equations do incorporate values for energy terms in the wave function. They do incorporate that in. The very first number talks about energy. And then you go down to shape and size, shape and size. And then you go down to orientation. And then you go down to spin. We'll get those again in a minute. 22, okay. Let's see, do I need 23? Nope, skip 23. 25. There it is. Okay, we are going to start talking about electrons in their positions around the atom. How many f orbitals have the value n equals 3? So let's go back to those 4 principal quantum numbers. Every electron has one set of 4 quantum numbers, right? Principal number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. So what can n have? N can be 1, 2, 3, out to whatever. And that relates to energy. The angular momentum quantum number will take any one of these and start with 0 and go up by whole number increments up to n minus 1. So what that means is, since we're starting at 0, the number of L's you can have is equal to the value of n. Right? So if you have 3, then you can have a 0, 1, and 2. You have 3 levels. Okay. How about n sub L? You take L and start at minus L and go up to 0 and then go up to plus L. Okay. So 1 can only have 1 n sub L. 1, 0. 0 can only have 1 m sub L. 1 can have 3, minus 1, 0, plus 1. 2 can have 5, -2, -1, 0, +1, +2. So forth and so on. And then m sub s is the easy one. It's either +0.5 or -0.5. And these are all sublevels of the ones above. So let's look at this problem again. 25. n equals 3. So we're focused on n equals 3. So now what are the possible L's can we have? We can have 0, 1, 2. Okay. Remember the L's, to make things not so messy with numbers, the L's get letters too. So the zeros are S's, the ones are what? P's, 2's are D's, and 3's are F's. But 3 doesn't go that high. That's as high as it can go. So n equals 3, there are no F's. Okay? Sort of a trick question. That was 25. Let's see, do I do 26? No, skip to 27. 27. I'm going to leave those there because we're probably going to need them again. If n equals 2, how many orbitals are possible? So now we're going to be n equals 2. How many orbitals? So how far down do we need to go to find out how many orbitals? Down to here. Because when you put an electron into an orbital, it can either be this or that. So this is not an orbital. This is down to here is your number of orbitals. Actually, I would call this an orbital, and this is a suborbital, or a shell and a subshell. Anyway, if we're starting at 2, what can we have here? Right? We can have 0 and 1. Right? We can have an S and a P. Then how about this one? How many can 0 have? Right? These are subshells. 0 can only have one m sub L. 0. Right? -0 is 0. That's as far as you can go. How about P's? You can have -1, 0, +1. So we have 4 orbitals here that you can have for 2. N equals 2. So that's why, where am I? Here, n equals 2. Yeah, how many orbitals? You can have 4. All right. These problems are just exercises in learning the procedures. Right? We haven't even started to build atoms yet. 28. I better scroll that. I need 29 also. There we go. So 28 says a given set of p orbitals consists of how many? That's misleading. P orbitals consists of how many orbitals? I would say p orbitals, a given set of p orbitals consists of blank suborbitals, right? Because you're going down another level. So p orbitals, where are we p? Let's see, p is 1. So 1 can be broken into 3 sublevels. Right there. Okay, answer C of that one. 29. Check my peanut gallery. Okay, no new faces. Which of the following is an incorrect designation for an atomic orbital? Okay. So now let's take a look at it. 1s, is that valid? Yeah. If this is 1, then you can have a 0, which is an S. That was good. How about 3D? 3D. So 3 can have 0, 1, and 2. 0, 1, 2. And 2 is D. So that's good. C, 1p. So can you have a p out of 1? Now, 1 can give you 0 here. That's an S. There are no P's. So that one's wrong. And that's C, right? Yeah, that one's wrong. 4F, yeah, you can have a 4 here, which means here you can have S, P, D, and F. So 4F is valid. And 6S, can you have a 6S? Sure. Start with 6, you can have 0, 1, 2, 3, 4, 5. So you can have an S at 6. In fact, you can have S everywhere. Okay, that was 29, 31, 2, 3, and 4. If I move too fast, stop me. 31. Okay, a point in the wave function, let's see. I'm going to leave that there because it looks like some of the future ones are going to need that. So let me just let's remove this stuff for now. There we go. And answer 31. How many, a point in the wave function where the amplitude is 0. Right, so I think they're referencing here. Remember the wave function you could say for, this is probability and this is energy. So for a d orbital, it would look kind of like this. And then for a p orbital at that same n level, would look more like, so it would be up here. Now I need a principal quantum number to do it this way. Let me back up. By definition, if your amplitude is 0, you're at a node. The amplitude simply is reference to the probability of finding an electron there. So that's our psi number squared. Okay. So if the wave function is 0, at that point, you're at a node. That just means the probability of finding an electron with that energy is 0. Okay, 32. I should have just made that a definition and let it go. How many electrons in an atom can have the quantum numbers n equals 3, L equals 2? Here we go. N equals 3 and L equals 2. Is that possible? 0, 1, 2. Yep. So that's true. So how many electrons can that have? Well, we're going from here, there to here. Now we branch out from here. So we can have -2, -1, 0, +1, +2. And each one of these suborbitals can have 2 electrons, +0.5, -0.5. So that's 5 times 2 equals 10 electrons. Right here. Now, where do we see 10 electrons? Where's the evidence in the periodic table? Right here. D orbital is being filled. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's D orbital filling, 10 electrons. Maximum. Okay, 33. How many electrons can be described by the quantum number n equals 3? Okay, n equals 3, L equals 3. N equals 3, 0, 1, and 2 is it. You can't have any electrons with that quantum number because L only goes up to 2, 0, 1, and 2. Right. Another trick question. Keep you on your toes. Oh, that was 33. 34, yeah, we need to look at 34. What is the L quantum number for a 4s? The L quantum number for 4s orbital. 4, right? 4. Oh, it's the same quantum number for every s, right? 0. I was overthinking that one. It's a good way to give your brain whiplash. That's why the answer is B. It's 0. It's always 0. All s's are zeros. Let's see, skip 35. Let's see what we're going to start with the next one. 37. Let's see. There it is. Which of the following combinations of quantum numbers N, L, M sub L, N sub S do not represent permissible solutions of the Schrodinger equation for the electron in the hydrogen atom? Well, the electron in the hydrogen atom can be any level. You can excite it up to infinity. N equals infinity, right? Then it'd be an ion. So these numbers out here, as long as they're positive values, any one of those could be right. But we have to go to the next level, right? Are there any here that we can eliminate? Yep, that one right there. No such thing as a negative L. So let's see. A, B, C, D, and E. So we've eliminated C. Can't be. Negative L's don't exist. All right, so let's look at the others. How about 9, 8? Is 8 possible? Yeah, 0 through 8. That's good. 8 and 2. Yeah, that's true. Could be. 0, 1, 2 on up. 6 and 5. 0, 1, 2, 3, 4, 5. Yeah. So all those L numbers are correct. So we move to the next level. How about this one? If it's 8, can we have a 4? Minus 8. Oh, yeah, we got a minus 4. How about this one? 2 could be minus 2 up to plus 2. That's okay. 5 could be minus 5 up to plus 5. That's true also. So we got to go to this level. Let's see. Which combination is not allowed? Okay. So this is allowed. Right, plus a half. Oh, we already found our answer. I'm wasting your time. C is not allowed. Duh. Okay. $37, $40. Oh, memory game. Right, be careful about this one. Who was the first chemist to recognize patterns in chemical properties of the elements? At least the first one that we discussed. I'm sorry?
B.
Newlands?
No, D. Couldn't spell it.
D.
Yeah, I couldn't spell it. You said it earlier.
Dobereiner.
Yeah, that one.
Okay, that's true. Right? What did he talk about? A single word starts with a T. Triads. Right? 3 groups of 3 elements that shared chemical properties. But you got it right anyway.
I remember you talking about
40, and then let's go to 41. Oops, too far. There we go. Another periodic table question. Why is Mendeleev given most credit for the concept of the periodic table of elements? I pushed this one kind of hard too. what was it about Mendeleev and his table that, actually think of it this way. Which one was, remember the two guys, Lothar Meyer and Dmitry Mendeleev, came up with the periodic tables. Which one was more useful? Mendeleev. Why? Because he used it to predict the existence and characteristics of unknown elements. That was sort of a, he said, all right, I'm going to go out on a limb here. There's a missing element here. Let's see, where's a good example? Tellurium and iodine. If you go by weight, atomic weight, then iodine should come before tellurium, because iodine is 126.9 and tellurium is 127.6. It's a small difference, but significant. So Mendeleev says, if he had iodine, they hadn't discovered tellurium yet. So he had iodine. Said, all right, iodine should go here if it's in order, but no, it doesn't have properties of the chalcogens. It has properties of the halogens. So he said, I'll skip it over here. And then he predicted the existence of this, its weight, other characteristics. Now, I'm not sure how he did that, but he did it. And the fact that he skipped that position and said there's an unknown element there that somebody's going to discover is why he gets the lion's share of the credit for this periodic table. I think it has something to do with his understanding of Canizaro's work and the concept of the mole. I would be willing to bet a sizable amount of your money for that one. Let's see, 44. The complete electron configuration of 10. Okay, now we can do what? We need the space. 44. Okay, we're talking about 10. So the symbol for 10, one of those oddballs.
No.
It's Latin.
Latin.
Think of toothpaste.
What?
Stannous fluoride. Get him.
No, give it to me. Dang it.
SN for stannum. Okay, now we need to know how many electrons are there in the neutral atom. So we look for the protons. 50. 50 protons means 50 electrons. Okay, so if you don't have it memorized, the order of increasing the energy for orbitals, then use that diagonal chart. Or you can go from the periodic table. Okay. As we build 1s, 2s, 2p. If we fill all the 2p's, we're all the way over here. Then we go back to the 3's. 3s, and then across to the 3p's. And if we fill all the 3p's, we're down here. Then we go down to the 4s. I might snake around. 4s, then where we are, we're in transition metals. Those are D's. But we can't have 4 D's yet. We haven't filled the 3 D's yet. So we go 3 D's. Fill those up, and that puts us over here. Starting with gallium. Now we're back to 4, the 4p. And there's 10 right there. So 10's got 4p, partially filled. So the rest of these are full. S's have 2, right? Plus 1/2, minus 1/2. 2, 2. These can have 6, 2, 6. Right? Why are the P's have 6? Because they have minus 1, 0, plus 1. Subshells, and each one of these has 2 in it. Okay? 6, 6, 2. How many in these? We'll just count out how many elements there are. There are 10. D has a maximum of 10 electrons. Now, how many do we use up? Let's see, 2, 2, and 6 is 10. 2, 2, and 6 is another 10, so that's 20. Right? Another 10 is 30. What did I do wrong? Oh, I need to keep going. Sorry. I'm filling in too soon. 4 P's are here. 10 is in the 5. So we fill up the 4 P's. Let's just keep going. 10, 6. Next is what? Snake around, 5 S's. And then you get into the transitions again. So we've already got 3 D's filled, 5 S's. We know that transition metals have to be filled with D orbitals. So the next one is 4D. That's 2, 10, and then 5P. So 10 is in the P group. We're filling P orbitals in here. Okay? So now I should have, let's see, 10, 20, 30, 40, 8, 2. Okay? Let's see, is that right? Yeah, when we get to 5P, 5P1, 5P2. This is where the P's start. 1, 2. So that's the complete. There we go. That's the complete one. So the easiest way to answer this one, I'd work backwards. Who's got 5P2 up there? Well, that one does, and that one doesn't. So that means B is out. Let's see, what's next? 4D10. All right, 4D10, those are 5D10. They can't be, so it has to be this one right here. Well, we check to be sure. 3, 4, 3, 3, 2. Yeah, that's it. That's D. Now, what's another way to write this? In shorthand. Well, you go 10, you work your way backwards. Like this, and snake around to the next period. Krypton. Krypton is the nearest noble gas. Kr36. So let's see. Kr36 would be, we will have filled our 4 P's. So that's where it stops right there. So what we have left over, 5s2, 4d10, 5, 2. Here you go. So that's a shorter shorthand. This is the core. Well, actually, this is a core. And how about valence electrons while we're on the topic? How many valence electrons in this in 10? 2 plus 2 is 4. Unless you're one of the unfortunate kids in schools today and learning new math. 2 plus 2 doesn't equal 4 anymore. Unless it's fingers. 2 fingers and 2 fingers is 4 fingers. I like to see them get around that one. Okay, 44. Let's see. No, we don't need 45. So I'm going to run out of time, of course. In fact, I did run out of time, didn't I? No, 12:30. 1:45. 1:45. I'm just going to have to keep going, whether you're here or not.
Well, I gotta go. I have patients. I already got a text.
Okay. Let's see. I might have to skip one. Let me see. 6. We'll make it quick. 46. The statement that the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle. First of all, what's the Pauli principle? It says no 2 electrons in any atom can have the exact same 4 quantum numbers. They have to be different in at least one of them. Okay, that's the Pauli principle. the one that says the lowest energy configuration is one with the most number of unpaired electrons in an orbital is Hund's rule. Right? For instance, oxygen. 1s2, 2s2, 2p, 2, 4, 4 more left. That would be the overall, but inside that p, you've got 3 levels. And these 4 electrons go in like this, 1, 2, 3, then you can go back and pair. The maximum number of unpaired electrons is the lowest energy. And it's logical, right? When you start pairing electrons up, they're in close proximity, and they may have opposite spins, but they still repel each other. So that's a higher energy than if, say, we had another orbital out here, different orbital. Okay, 46, probably 47 also. Yeah. Okay. I may just have to. I told them not to schedule that meeting while I'm in class, and they did it anyway. So I just might have to skip that meeting. An element has the electron configuration of krypton 5s 4d. Where have we seen that one before? That's 10, right? So if this question is standing alone, you just find that element. So you start at krypton, okay? You got a full 5s, you got a full 4d, and then a 5p, 1, 2. So now you're right there. So what is that? That's a metal, right? It's a metal. 48. An element with the electron configuration of xenon, 6s2, 4f14, 4 and 5d7. 5d7. Oh, right. These, recognize that these are full. S has 2, F has 14. Right. Count these letters up there, 14 of them. So that's full. If you have F with 14 electrons. Then you go to D, and it's only got 7 in it. Right? D is going to have 10. So we're still in transition elements, transition metals. Right? So that's why A is the answer. You can tell from the electronic configuration where your element's located. Okay, 49. Yep, 49. All alkaline earths have the following number of valence electrons. Remember when we were writing formulas, right? Type 1 compounds where you just balance the charges. And the metals have fixed charge. This is one of those, alkaline earths. So what do we say was the charge on an alkaline earth? +2. Right? +2. And it's +2 because it has 2 valence electrons that it's willing to part with. So if it gets rid of 2 electrons, now it's a +2 imbalance. Right? So number of electrons, 2 for alkaline earths. And that makes sense because it's the second column in the S-filling region. That means it's got 2 electrons in the S orbital. Okay. Yeah, we're 150. Ti. Titanium. Titanium has how many electrons in its d orbital? All you need to do is go to your periodic table and say find titanium. Right? D orbital, D1, D2. It's got 2 electrons. 2 electrons. Let's see, which D is that? 3D. 3D2. Now there are exceptions. When you get right here in the middle, let's see, 1, 2, 3, 4. Right in here, chromium and magnesium. That's one of the anomalies. That's one of the anomalies that I think I've got a question in here to talk about that also. 15. No, skip 51. Iron, 52. There we go. Iron has how many electrons that are unpaired in its d orbitals? So iron has, it's a 3D, 1, 2, 3, 4, 5, 6. 3D6 is the highest level, energy level with 6 electrons in it for iron. So remember, I've got 1, 2, 3, 4, 5. So they go in according to Hund's rule like this. 1, 2, 3, 4, 5. Now we can pair them up. There's only one pair. So we have 4 unpaired electrons in iron's d orbital. Now, this problem says unpaired in its d orbitals, plural. But iron only has one d orbital. If we put an element in there like, well, go down one. Ruthenium. That would be 4d6. So ruthenium already has this one filled up. So it's got 10 plus. Well, actually, unpaired in its d orbitals. That'll be the same answer, right? Because this one's already paired up all the way across. Okay, so chasing my own tail. Okay. All right. 52. Okay, 53 and 4, they're good answers. They're good questions. 53 and 4. Scroll a little bit. $53. Another reason I want to finish this, complete this, is on the Greenbrier campus yesterday, their internet was in and out. So my recording just no good. So I want to get this done for their benefit too. Okay, which represents the ground state for nitrogen? Nitrogen has 7 electrons. Okay. The ground state, 1s is already filled. That's why it's not on there. So we have 2s and 2p. Right? So we have 2 here. That means 3 left over. There we go. But they want us to know, to tell something about these. So this one has 2 electrons like that. This one has 3 like that. So which one shows that? It's this one, E. Okay. 54 takes this one and makes an ion out of it. Add an electron. Ground state for the N- ion. So we need to add an electron, which means now we have 8 electrons. That means we're going to have 2p4. So now we have to pair them up like that. So that looks like oxygen. In fact, this ion is isoelectronic with neutral oxygen because it has 8 electrons just like oxygen and the same electronic structure. So which one is that? Let's see. Wait a minute. No, this one is A. I'm sorry. I was looking ahead. 53 is A. 54 is E. Sorry for the confusion. Okay. 54. 55. Let's see, where's 55? There's 55. In which group do all of the elements have the same number of valence electrons? So, which ones will have the same number of valence electrons? Well, if every element in these triads comes from the same group or family of elements, they will have the same number of valence electrons. So we look through the periodic table, we find that none of them all come, each triad, none of them come from the same group. There might be two from the same group and one oddball, but none of them come from the same group, so none of them have the same number of valence electrons because they're all neutral, right? We don't have any ions in there to muddy the water. So 55 is E, none of these. You just have to look at the periodic table and see where they are. 58. Oops, too far. Okay, 58. Of the following elements, which has occupied d orbitals in its ground state neutral atoms? Which has d orbitals? Now, that doesn't mean that the d orbitals are being currently filled. They can be filled d orbitals. So we look and see. Okay. Look at the period that each one comes from. Calcium is in the fourth. Let's see, barium. Let's just put them up here. Barium, calcium, silicon, phosphorus, chlorine. Barium is down at 1, 2, 3, 4, 5, 6. It's the sixth period, right? So it starts off, well, it will have 6s2. So if you back up, you're going to run into d orbitals. Several of them. So it does have occupied d orbitals. Barium. Oh, we found our answer because there are no weird ones in here. But if you look at calcium, calcium is 4s, right? What's next? The first 3d is beyond calcium. Right? So calcium has no d's. Silicon, it's actually 3p's. It hadn't got the 4s yet, right? So it has no d's. Phosphorus, silicon, and chlorine, they're all in the same boat. 3p's, no d's. Right? So barium is the only one that works. That's 58. Let's see. 59. Of the following elements, which needs 3 electrons to complete its valence shell? 59, did I say? Which needs 3 electrons to complete its valence shell. In order to do that, I would look at where those elements are, left or right. To complete its valence shell, barium's already got its completed valence shell. It's this 6s. So in order to go to a desirable filled shell, it loses those 2 electrons. It's not going to pick up 3 electrons. So no metals, right, no metals work here. Barium, calcium, and silicon is non-metal. So silicon, phosphorus, chlorine. So how many electrons does it take to make them look like a noble gas? Silicon is in carbon's group, takes 4 electrons. Either way, add or subtract. Phosphorus. It's next door in the nicogens. It takes 3 electrons to make phosphorus look like argon. Phosphorus is your answer. Because halogens only need 1 electron. So phosphorus is the answer. That's 59. Not 60, 62. Scroll. Okay. 62. How many of the following electron configurations for species in their ground state are correct? Okay. So, I'm sorry? Oh, yeah, I chopped one off there. There we go. How many of the following ground state correct? Okay. So we just have to look at the electronic configuration of each one, and the periodic table is the best place to go for that. Calcium needs, let's see if it's in the right order. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Calcium's in the 4th period. That was correct. And in its ground state, yes. Okay. Magnesium. Magnesium is an alkaline earth. It needs 2 s electrons. So regardless of what this says, it's wrong. Vanadium. Vanadium is 3 over 3 Ds, 3D3, but that's wrong. It's a 4s2 and a 3D3. Okay? So 1 and 3 are wrong. How about 4? Arsenic. If we go from arsenic backwards, there's arsenic. Backwards, we get to argon. Okay, that's right. And then we keep going from argon, that's 4s2, 3d10. And then arsenic is 1, 2, 3. It's in the phosphorus group. Yeah, that's right. And phosphorus is 1s2, 2s2, 2p6, 3p. 3s2. No, that's wrong. 2p6. Now, we went straight from this p to that p. That can't be. We skipped an s. Right, so how many is it? 3 of them? Yeah, 3 of them are correct. Let's see, let's skip down to 66. Is that right? 66. Yep, 66. Oop, I've only got 1 zoomer left. Which of the following is the highest energy orbital for a silicon atom? Well, all you have to do is just look where it is. Where's silicon? It's right here. So this is the 3rd period, means that's a 3p. 3p2, 3p, here we go. That's the highest energy orbital for a silicon atom. 3p. 60, 7, 8, 9. Okay, let's do 7. Oh, definition time. Which of the following processes represents ionization energy of bromine? Okay, so we got to have the symbol. What are we going to do to ionize bromine? We're going to make something with an electron. Right? We got to pull that electron off of the atom. But it's important that we start from the correct phase. bromine, monatomic bromine in the gas phase. Can't let it be diatomic, and you can't let it be a liquid, because it takes energy to break that up. We want to know how much energy does it take to remove that electron. In order to do that, we've got to go up to gas phase. And then what we have left over is the +1 ion in the gas phase. Okay. So that by definition is C. That's the ionization energy. 67, 68. What are the elements? Sulfur, chlorine, fluorine determines increasing ionization energy. All right, so what's the trend of ionization energy? And we have to assume that they're talking about first ionization energy. We take these as ground state neutral atoms. The trend is lower left to upper right. So which one is the farthest left? Out of those three, sulfur is the farthest left. Then which one's farther down after sulfur? Chlorine, and then fluorine is at the top right. So that should be the order. Sulfur, chlorine, fluorine for ionization energy. 69. Yes, 69. 69. So the trend for 69 is atomic radius, increasing atomic radius. So what's the trend for atomic radius? Increasing from upper right to lower left. Right? So it increases in size going down, increases going to the left, or decreases going to the right. So if we're increasing, we need to go to the top right and move to the left. All right, we've got the same three elements. So we just switch them around. Right. Upper right, lower left. Okay. Let's see, who's next? 73. Scroll time. Okay. Of the following elements, which has the lowest first ionization energy? It's that trend again. So which one's the lowest first ionization energy? It's the one that's farthest to the left and toward the bottom. And out of all of these, barium is it. Uh, 70. Oh, yes, 74 of the following elements. Which is most likely to form a negative ion with charge 1-. Actually, that's pretty simple. Most likely to form an ion with a -1 charge is a halogen. So we got a halogen right here. That was too easy. Let's see, what's the next one on the agenda? 75. Which of the following atoms has the largest ionization energy? Well, this is kind of beating the same dead horse. Largest ionization energy, we need to find the one farthest to the right and up. And that's neon. Neon's got two things going for it. Not only is it trending lower left, upper right, but it's also a noble gas. It's really hard to get an electron off a noble gas because they have all full shells and they're just perfectly happy the way they are. They don't ionize well. $75, 77. Which has these types of electromagnetic radiation arranged in order of decreasing frequency. Decreasing frequency is decreasing energy. Energy equals Planck constant times frequency. So if the frequency decreases, you have lower energy. So I look at it that way. What's the highest energy possible here? Decreasing highest should be on the left-hand side. There's gamma. Gamma is the highest energy we know of. And then microwaves. No, that's the wrong order. Right, so it can't be this one. So what's the next highest? X-rays? X-ray, visible, ultraviolet. Nope. X-rays, then ultraviolet, then visible. Can't be that one. How about ultraviolet? Visible, infrared. There you go. Decreasing energy, which means decreasing frequency. '77, let's see. Got so many. 78. Which of these types of electromagnetic radiation, arranged in order of increasing wavelength? Increasing wavelength is decreasing frequency. It's the same as the one before. Ultraviolet, visible, infrared. That was easy. Next. 79, 80, and 81. Okay, 79. Which of these types of electromagnetic radiation is arranged in order of decreasing energy? Well, we're saying the same thing 3 different ways, right? They're all C. All right, is 80 on the agenda? Yep, 80 and 81. The quantum theory, in the quantum theory, the magnetic orbital momentum quantum number, which is m sub L, is most directly associated with which property of orbitals? Right, remember, energy is N, L is shape and size. M sub L is orientation. So B is the answer. A1. In the quantum theory, the angular orbital momentum quantum number is most directly associated with which? One. I just said that one actually. It's most closely associated with shape. Right, so S orbitals are spherical. P orbitals are dumbbells. D orbitals are a mix of elongated dumbbells and with one donut in there. And those are mathematical representations. It's not like we've seen them. That's what we put the equations into a computer and it spits out a model. Okay, 84. Scroll again. Okay, here comes an anomaly. 84. Select the correct electronic configuration for copper. Okay, how many electrons in neutral copper? 29. Okay, notice that we're in shorthand. So if we go from copper and back up to argon. And argon has 18. So now we need, well, if we go from argon and wrap around, the next one is 4s2. And we go through 3d something. This is 20, that means we have 9 electrons left to go. Okay? Problem with that is, that's not the lowest energy state for this atom. The lowest energy state, since it's so close to being filled Ds, it will steal an electron from the S. And it looks like this. A filled D orbital is lower energy than a filled S orbital, 4s orbital. So it takes an electron. This is an anomaly. It's the next to the last element in the 3D transition metal filling. Okay? So that's the trick for this one, to recognize that that one is not going to obey what we consider to be the rules. It actually does obey the rules. It's the lowest energy configuration of electrons. And this happens to be it, not that one. Okay, 85, I think, is probably part of the mix. Yeah, 85, 6, 7, and 8, actually. 85, okay, another definition. How do we write the electron affinity for X? Well, it's got to be neutral, and it has to be a gas. An electron affinity is attraction of an electron. So we're going to add an electron to this neutral atom and make a negative ion. And what do we get out of that? Well, it doesn't show it here, right? The answer is C. But what do we get out of that? We get energy with a negative sign because it's exothermic, right? If electrons move from infinity to a position in the atom, it's automatically exothermic, gives up energy. And the more negative, the more energy it gives up. So the more energy it gives up, the more negative the number, the stronger the attraction. All right. 85, I think. I said 86 also. Let's roll it. Here we go. Which of the following lists of atoms are arranged in order of decreasing atomic radius? 6. Decreasing atomic radius means lower left to upper right. Right? Increasing is upper right, lower left. So lower left to upper right. So we look at the ones that we have, and they're not real friendly, are they? These two have the same elements. These have the same elements. Those have the same elements. These don't. These don't. Right. So since we've got unique selections for each one, we just work our way down until we find the right answer. Lithium, oxygen, nitrogen, fluorine. Lithium, oxygen, that's decreasing. Nitrogen goes back up. Okay, so that one can't be it. Oh, wait a minute. Lithium, oxygen, nitrogen. Yeah, that's right. That's the wrong word. Lithium, nitrogen, oxygen, fluorine. So they're in the same period. So now we can go from left to right. Right? So lithium, nitrogen, oxygen, fluorine is right. From left to right, this is a bigger ion, a bigger atomic radius than this one. It's bigger than that, bigger than that. So that's B. That works. Uh, 87, I think. Yeah, 87. This is going to take some calculating. All right. Consider an atom traveling at 1% of the speed of light. So its velocity equals 0.01 times 2.9979 times 10 to the 8 meters per second. Which is really, let me just save myself some writing. Ten to the 6th meters per second. So that's the velocity. 1% of the speed of light. The de Broglie wavelength is 1.46 times 10 to the minus 3 picometers. But what's a picometer? 10 to the minus 12. Okay, so in meters, we know we're going to have meters eventually. So in meters, it's 1.46 times 10 to the minus 15 meters. All right. Which element is this? Okay. How do we find out what element we got? Well, if you know the number of protons, it's easy. But I don't think we can get the number of protons out of this data. But next best thing is molar mass. So what do we need for molar mass? And my abbreviation, of course, is 1 kiloweight. Molar mass, we need mass per moles. So let's see, what do we got here? Well, we know one atom. This is the wavelength of one atom. Excuse me. Yeah, one atom of that element has this wavelength when it's moving that fast. So we know it's so much mass per one atom. We just got to find out what the mass is. So we need the de Broglie equation, right? Wavelength equals Planck's constant over mass times velocity, right? If memory serves me. And this is 6.62, or is it 3? 626? I have to look it up. Oops. I know what I'm looking for. Yeah. Times 10 to the minus 34. 4 joule seconds. Okay. Mass is our unknown. And velocity is 2.9979 times 10 to the 6th meters per second. And wavelength is 1.46 times 10 to the minus 3. Oops. 15 meters. Okay, so this is equal to that calculation. There's our unknown. So if we bring the mass over here and the wavelength over there in its place, we just divide this into that and that into that product or that quotient, or multiply these together and divide it into that. And that should give us the mass in kilograms. Now, I think I mentioned earlier in the semester, how do you get kilograms out of this? I don't see any kilograms. It's buried right there in that. 1 joule is a kilogram meter squared per second squared. So this cancels the 2 second terms. This cancels, let's see, squared. Oh, there's a meter and there's a meter, cancels those, leaves us with kilograms. So we're good on the units. We just have to do the calculation. So where's my calculator? So I'm going to take this one, divide by that one, 6.626 exponent negative 34, and 1.46 exponent minus 15, divide that, and then 2.9979 exponent 6. So I get mass of our atom is 1.5235. Hang on to a few decimal places just to avoid rounding error. 25 kilograms. And that's for one atom. Right? So this is per atom. Okay? This is in units of grams per mole. So now it's a dimensional analysis problem. Convert kilograms to grams. And convert atoms to moles. 6.022 times 10 to the 23rd atoms is 1 mole. So now we have grams and moles because atoms cancel atoms, kilograms. So we say this, whatever I got in my calculator here, times 1,000, and then also times 6.022, 10 to the 23rd, and I get 91.7. So molecular weight, 91.7 grams per mole. Go to our periodic table and look for 91.7. And close. Closest one I can find is zirconium. If I did that calculation right. Well, that's what it says. So the nearest one I can find is zirconium. And if there were discrepancy, it would have to either be, probably be niobium, because it's on the high side from zirconium. And niobium is not a choice, so zirconium is the only one possible out of that group. Okay. That was kind of tedious, but it really wasn't that hard. All right, 87, 88. Scroll it. Let's see. An investigation of the electronic absorption spectrum of a particular element has found that a photon having wavelength 500 nanometers, wavelength of 500 nanometers, provides just enough energy to promote an electron from a second quantum level to a third. There's 1, 2, 3. From a second to a third. So it's going to move up to here. From this information, we can deduce what? What does it take? Well, this light energy has to be just enough to promote. It absorbs, the electron absorbs energy of that wavelength. And from this information, we can say the energy of the n equals 2 level? No. No. N 2 and 3? No, we can't tell that. The sum of the energy? No. The difference of the energies. The difference is that's what that's equal to. H nu equals actually not just E, but the change in E. All right. 88. And 90. Oops. Scrolls on the chart. Okay, we're going to need that table. There we go. 90. We're going to use energies of those levels. The reason I put it this way is so that you didn't have to waste time during a test using a formula to calculate those energies. You just need to know what it means. The wavelength of light that is emitted when an excited electron of hydrogen atom falls from n equals 5 to n equals 1. So the change in energy is what we want to find. Then we can equate it to energy in the Planck's equation. So the change in energy is always final minus initial. So the final energy is n equals 1. Goes from 5 to 1. The final is minus 2.178. Minus 2.178 times 10 to the minus 18 joules. And then minus 5. Excuse me. Hold on a second. Final minus initial. Yeah, this is initial. The initial is 5. Minus 0.08. 712 times 10 to the minus 18. Notice how nice I am. I keep the powers equal, so all you have to do is subtract these two. And then it's times 10 to the minus 18. Well, actually, this becomes a plus. So you add that one to this one, which you get the point. So we only need 2.178, change sign and then plus 0.08712, and that's 2.091 minus 2.091.
Infinity and this is joules.
So that's equal to, that change in energy is equal to Planck's constant. 6 point, yeah, that's not. Right. Yeah, that's Planck's constant. 6.626 times 10 to the minus 34 seconds. Times frequency, or we can write wavelength in terms of 2.9979 times 10 to the 8 meters per second for C, and then the wavelength is here. So if we move the wavelength over here, and the joules over there, that calculation will give us our answer. 2.9979 exponent 8, and then divide by 2.091 exponent minus, and then times 6.626 exponent negative 34. So I get, we're going to have to use absolute values here. Otherwise, we get a negative wavelength. That will do. We just have to, the negative tells us that energy is being emitted. But it's this wavelength, it's 9.4, 9.50 times 10 to the minus 8. So if we want to put that in, oh, it's in meters, that's fine. Meters. 9.5, 10 to the minus 8, here we go, B. I thought I was going to ask for nanometers. This would be meters. So nanometers is 10 to the minus 9. So we need to move this to the right. 95.0 nanometers. Wait a minute. No, other way. No, I was right the first time. To the right. Let's make this one bigger. Power has to be less. This goes up, that goes down, then this one together is minus 9. There we go. Yeah, 95 nanometers. Okay, that was 90. I almost get 93. That's just rehashing. So 93, you can look at that one if you want. Useful information, work problems. I'm going to go to 94. There it is. If this is a representation of the 2p orbital, what can we say about it? We're describing the electrons in the p orbital. The electrons move along the outer surface of the p orbital in a figure 8. I don't think so. The electrons move within the 2 lobes of the p orbital, but never beyond the outside surface. That's not true either. This is roughly a 90% probability of finding electrons there. The electrons are concentrated at the center node of the 2 lobes. Well, that is a dead giveaway there. You don't find any electrons at a node. The electrons are only moving in one lobe at any given time. Oh, well, I'm reaching for fillers here. The electron movement cannot be exactly determined. That's true. That's it. 94, 95. Let's see, do I want to do 95? How many electrons can be contained in all orbitals within n equals 4? All right, we'll do this one. 95. I need the marker. Okay, if n equals 4, what can L be? L can be 0, 1, 2, 3. M's of L, for this one can be 0. For this one can be -1, 0, +1. For this one can be -2, -1, 0, +1, +2. And for this one can be -3, -2, -1, 0, +1, +2, +3. Okay. And then below that, what do we have? Oh, below that we got spin 2 electrons each. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16. Skip one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 times 2 electrons each. 32 electrons. An occupier n equals 4. We lost everybody. Let's see. All right. Now, we can dispense with 96 pretty quick. The small but important energy difference between 3s, 3p, and 3d orbitals are due to magnitude. Remember those drawings of the orbitals on the same graph where we have probability here, energy there. At the 3 level, D looked more like this, and then P looked like kind of like that. And S looked like this. Okay. What we were demonstrating was penetration. The S orbital penetrates down below the D and the P. So that slight difference in energy, the difference among those 3 orbitals is due to the penetration effect. Let's see. Uh, 97 is just skip it. 98. I see. You can look at these on at your leader. 97, 98. I'm trying to save time here and not duplicate efforts. 101. Let's do 101. Oops. One is going to just demonstrate 2 things. An element E has the electronic configuration. That's 10. 10. Has krypton, and then 5s2, 4d10, and 5e2. Okay. The formula for the fluoride of E is what? So if we have E and we combine it with fluoride, fluoride is going to have a -1 charge. So what possible charge could E have? Well, we look at the valence electrons. Right? We have 2 here and 2 here, so that's 4. It all depends upon how strong the anion pulls on electrons. If it pulls strong enough, it'll get all 4 of those valence electrons. That's why we picked fluorine. Fluorine is the most electronegative element in the table, so it's going to get all 4 of them. But it takes 4 fluorines to do it. So if this is going to be a 4+, that means we need 4 fluorines. EF4 would answer that question. Now, we don't have EF2 up there, right? So there's no confusion there. If we used a different element, like bromine, that has less strong pull on electrons, maybe it only gets these 2. And that would be EBr2. But in this case, fluorine, as strong as it is, an attractor, EF4 is your best bet. And it's all based upon valence electrons. Those are the ones that are involved in chemical reactions. Let's see. Okay, 104 is valid. We'll look at 104. Second ionization energy. Which of the following atoms would have the largest second ionization energy? So what does it take? The general rule is the largest second ionization energy is one where the atom dips into its core. It's used up its valence electrons. That is, if you don't have atoms where you're comparing. Well, yeah, that's the only approach to this one. Just look for the one where you get into the valence. So the second means that the atom only has 1 valence electron, and that's sodium. Calcium has 2. Actually, sulfur, we could make arguments there, except that removing an electron from sulfur, you're still not used up all its valence electrons here, or here. Sodium is the best answer. That's the point of this question. You're getting into the core. So 104, 107. Here we go. Let's see. Do I want to mess with this? Which of the following concerning second ionization energy is true? Okay. We're comparing aluminum and magnesium here. So let's look at it. Let's look at aluminum and magnesium. Right. They're both in the same period. Magnesium is a 3s2. As 3s2 is its valence. Aluminum is 3s2, 3p1. Okay, so second ionization energy. If you remove one of these, now you're down to removing that last one. So you basically maybe 2 times energy to remove the second one. And this one, P comes off really easy. And then this one comes off maybe not even twice as much as that. So I think aluminum would be, second ionization energy would be less than magnesium. Let's see which one fits, if I got that right. Aluminum is higher than magnesium. No. Aluminum is higher. Aluminum is lower than that of magnesium because magnesium wants to lose the second electron, thus the interchange is greater. Aluminum is lower than magnesium because the second electron taken from aluminum is in a p orbital. No, the second electron is not in a p orbital. So it would have to be C. Right? One second. No, it says B. Hold on a second. Aluminum is higher than that of magnesium because the electrons are taken from the same energy level, but aluminum atom has 1 more proton. That's okay, that's right. 13 versus 12. So it'll be the other way around. It's all due to the protons. Okay, did I confuse anybody? Well, there's only one here. That was 107. Ooh, 108. Okay. You see, I'm going to need a formula for this. I don't have to run. 108. Let's see. Consider a planet where the temperature is so high that the ground state electron for hydrogen atom is N equals 4. So let's say the energy of our planet for the ground state electron is due to N equals 4. That's ground state. For Earth, of course, the ground state is N equals 1. And what's the ratio of ionization energy for the hydrogen on this planet compared to the Earth? So we're going to ratio those two. So the ionization energy here goes from N equals 4 to infinity. And here it goes from 1 to infinity. Okay? So if we just look at this as a sort of a qualitative approach, which one's going to take more energy? That one. So the ratio should have the denominator be bigger than the numerator. That's the first thing I noticed. Now, we need a quantitative value, a ratio. So here, so how do we calculate the energy of this one? In fact, the delta E for this transition, that transition, which would be the ionization energy, is that formula. Let's see, where's it? Never can remember this constant. Is minus 2.178 times 10 to the minus 18. And we have, since it's hydrogen, the Z is 1, minus, and this is final minus initial. So this is infinity. And initial is N equals 4. And it's squared. Okay? And the energy from this one on Earth is equal to that same constant times its calculation, which this is also infinity. Right? We're both going to infinity, final condition, minus 1 over 1 squared. Okay? All right. If we take this as a quotient, that term goes away. Numerator and denominator cancels out. This term is what? 1 divided by infinity? 0. 0. So this one is going to be what? 1 over 16. This is going to be 1 over 1. But notice, this is in the denominator. So this ratio to that is actually 1 divided by 16. And that fits our qualitative assessment. Right? Where this one's bigger than that one. It looked like it was going to be hairy, and it really was. Let's see. Go back to where it was. Let's see, skip down to, oh, that's it. That's all the ones I had marked.